So now let's move on to a second example. And again, we want to compare this parabola to our parent function, y is equal to x squared. So let me draw just a quick sketch of that parent function. This will give a rough idea of the function y equals x squared. And we want to know what happens when we subtract on what I like to call the inside of the function. So what I mean by inside is that it's going to be within these parentheses, and essentially we're going to be affecting x. And when dealing with the inside of the function or dealing with the x values, it's almost always the opposite of what you'd expect. So when dealing with the above function, when we added 2 on the outside, that shifted everything up 2 units. But when we're adding or subtracting on the inside, the opposite happens. So in this case, since we're subtracting 2, what ends up happening is that we're going to shift right 2 units. And the way I think about this is that you want to think about which x value makes this expression 0, or which x value makes y equal to 0. And in this case, it would be a positive 2. So that tells us that we want to shift essentially this vertex here over 2 units to the right. And that's what's going to happen to essentially every single point on this graph. So you're going to get the exact same looking parabola, it's just going to be shifted over 2 units to the right. So these should be the same picture, just shifted 2 units over. And let's try and make sense of this. For instance, this point right here, this is the point 1, 1 on the parent function, and notice it got shifted over to this point 3, 1. And that's because if you imagine putting in this x value of 3 into our function, that when it simplifies, you end up just getting 1 on the inside and squaring it. So putting in an x value of 3 into this function is the same thing as putting in an x value of 1 into this function. You would end up getting the same results. And we could make that argument with, let's say, 2, 4. It should be this point up here, 2, 4 on the parent function. So that point got shifted over to 4, 4, which should be somewhere maybe over here. I didn't draw it perfectly, but 4, 4. And notice if we put in an x value of 4 into here, into this orange function, then when we simplify it, we get 2 squared, which is 4. So we get the same value as if we put in x is equal to 2 in this function. So essentially what you want to notice is that every time you pick some x value here for this parent function, that if you pick the x value that is 2 bigger than that, you would get the same y values. So for instance, if I pick an x value of 5 here, when I square it, I get 25. But if I pick an x value of 7 over here, I should get the exact same y value because I'd have 7 minus 2, which is 5, and then I square it. So y would also be 25 here. So when I use x values that are 2 bigger in this orange function, I get the same y values in the green function and the orange function. So let's now go on to a third example. And now we're essentially just multiplying on the outside. So real quickly, I will draw in that parent function again, just so that we can essentially compare it to that and see what happens. And let's look at the vertex again, that point 0, 0, and we'll see that nothing's going to change. Namely, if we put in 0 here for x and we square it, we still get 0, and then times 3 is 0. So for our function, this green function here, it would still go through the origin at 0, 0. But now if we look at a point like, let's say, 1, 1, when we put in an x value of 1 and we square it, we still get 1, but then we multiply that by 3. So now our y value would be 3. So essentially, instead of being at 1, 1, it would be at 1, 3. And actually, let me use that green color. And the same thing would be true for -1. It would be at -1, 3. And if we put in an x value of 2, usually it would be at 2, 4, somewhere up there. But now, essentially, we'd have 2 squared, which is 4, times 3, which is 12. So that point would now be at 2, 12, so somewhere way up here. So essentially what happens is that our graph gets much skinnier. Or in other words, each of the y values from this parent function is now multiplied by 3. Notice that this point 2, 4 is now at the point 2, 12, where the y value is now 3 times greater than it was. So this multiplication in front, we say that it stretches the equation by a factor of 3. So if we were going to multiply it by 5, then all the y values would be stretched by a factor of 5. Now, if we were going to multiply something less than 1, but bigger than 0, then it's going to flatten it out. So for instance, if we have y is equal to 1/2 x squared, then essentially all the all the y values would be cut in half. So the parent function, that's the orange one here, so it should be all the y values are half that, so it would go through there. It would go through a 2, 2 at -1, 1/2 at -2, 2, and we can connect those. So that would look something like this. Again, this is a very rough picture. So when you multiply in front of x squared and the number is between 0 and 1, this doesn't stretch it, this shrinks it. Or you can think that it essentially flattens it out. So it makes it much wider compared to if we multiply by 3, that makes it much skinnier. So essentially, multiplying in front just affects the y values. So it's either going to stretch or shrink the y values. And if we were going to multiply by a negative number, all that does is it reflects it across the x-axis. So essentially, compared to this green function, if we put it in negative now, let me use a slightly different color so we can distinguish. So if I put a negative in front of it, that's going to essentially take this green function, any y value, like let's say this point 1, 3, is now going to be negative. So it would be 1, -3, so somewhere down there. So essentially, the entire function gets reflected about the x-axis. So when you see this negative in front, you want to assume that you reflect, and reflecting over the x-axis. So essentially, every y value is now becoming the opposite of what it was. And with all these examples in mind, let's do a more difficult problem. So with this problem, we have multiple different transformations going on. And let's start breaking them down one at a time. So this minus in front, we just talked about that. We will reflect about the x-axis. And then we have this 2 also in front. So that when we multiply in front of the essentially x squared term, then that's going to stretch it or shrink it, depending if it's bigger or smaller than 1. But in this case, since it's bigger than 1, we're going to stretch by a factor of 2. And then we look on the inside of our function. And remember, when looking on the inside, it's always the opposite of what you'd think. So I like to think, what x value makes this expression 0? And in this case, it would be a -1. And since that's a -1 that makes this 0, that tells me to go to the left 1 unit. And then lastly, on the outside of this function, I have this -3 here. And when I'm adding or subtracting on the outside, that just tells me to shift everything up or down. And since I'm subtracting 3, that tells me all my y values will be shifted down 3 units. So now that we have all of our transformations in order, what I like to do is start with the parent function, that y equals x squared, which we know has a vertex at the origin. And then I essentially just track what happens to that vertex. So the first thing we're going to do, it's going to reflect about this x-axis. But since the vertex is on the x-axis, it's not actually going to reflect because it's on the line of reflection. So for this particular point, it actually doesn't reflect. But if we were looking at the point 1, 1, that would now be at 1, -1. So every other point would reflect, but not the origin. So for this particular point, we ignore the first one, and then we're going to stretch it by 2. But again, we're stretching the y value by 2, but the y value is 0 here, and 0 times 2 is still 0. So this one and this one don't affect the origin. And then we're shifting it left 1, so that's over here, and then down 3. So 1, 2, 3. So that would be there. And since that point is actually on the graph, we've finished all the transformations. We can plot that in that same pink color to match up with our equation. And this right here is the vertex. And remember that since it's a negative on front, it flipped everything downward. So essentially we expect it to open downward somehow, but we first need to plot a second, possibly even a third point to figure out the rest of this curve. And what I do, once I find the vertex, I'm just going to plot a point right next to it. So I'm going to choose an x value of 0 and see what the y value is. So anywhere I see an x, I'm going to plug in 0. So I'd get 1 here squared, so it'd be minus 2 times 1 squared, which is 1, and then minus 3. So that's minus 2 minus 3, which is minus 5. So that would be all the way down here. And with parabolas, they're symmetric about the vertex. Remember, we can draw that line of symmetry down here. So if 0 evaluated to minus 5, it would be a mirror image on the other side of this line. So at minus 2, we would also get minus 5. Though you can test that. If you put in minus 2 here, you get minus 1 squared, which would be 1, and you'd end up essentially with this again. And now that we have 3 points, we can connect them. So we can draw our parabolic curve, and it looks something like this. So this will give you a rough idea of what this equation here actually looks like.